Hello there, this is Richard Walker from Elucidate. Welcome to another video on machine learning techniques where we're going to take a closer look at logistic regression. Logistic regression is used to estimate the probability that a sample datum belongs to a class, such as whether a loan applicant is more likely to repay or default on their loan. If the estimated probability is greater than some threshold, such as 0.5, then the sample belongs to the positive class, usually labelled as 1. If less than the chosen threshold, then the sample would belong to the negative class with a label of 0. We therefore need a function that will compress all of our input features down into a range between 0 and 1. This will represent the likelihood that our sample is in the positive or negative class. If you've seen Elucidate's video series on neural networks, you'll recall that the SIGMOID function maps values from -infinity to +infinity into the 0 to 1 range. If you've not seen these videos, there's a URL on the screen and a link in the description. In this video, we'll look at the SIGMOID function that squashes our input features into a range from 0 to 1, and then we'll use a simple example with a single variable to see how we can use the SIGMOID to classify candidate points. We'll then add an additional variable. Our SIGMOID function now describes a surface. Thirdly, we'll present a vectorized form of these equations to allow us to deal with as many inputs as we require. Then based on this, we'll train our logistic regression algorithm. We'll use the vector equation and tweak and nudge its parameters to get an optimum solution based on our training data. If you feel that this seems similar to how we train a neural network, then you're correct. We use stochastic gradient descent, or SGD, to nudge, tweak and optimize our parameters in logistic regression, much as we did with neural networks. In fact, the use of SGD for logistic regression is a little simpler than for neural networks, as we don't concern ourselves with things like backpropagation. This makes training a logistic regression solution quicker than a corresponding neural network. We finally compare our logistic regression solution to other machine learning techniques we've analysed, such as decision trees, support vector machines, and k-nearest neighbours. Here we see the sigmoid function. The equation is shown on the left of the screen and the function is drawn in red. As x approaches positive infinity, the sigmoid function asymptotically tends towards 1. Conversely, as x nears negative infinity, the sigmoid nears 0. Thus, the entire number line is compressed to values between 0 and 1 by our sigmoid. For our purposes, these values will be used to represent the likelihood that our sample is part of the positive class or negative class. If we look at how we apply this to our classification problem, we can plot one of our input features, in this case the debt to income ratio, on the x-axis. Here we see the general form of the sigmoid equation. Note that it has a couple of input parameters, a weight w and a bias b. We can alter these two values to adjust the steepness and position of the slope. As before, we can plot some of our training data on this chart. The red dots represent samples that have defaulted and the green dots represent repaid loans. To better illustrate how the sigmoid function aids classification, let's show the red dots as having a probability of default as 1 and leave the green dots where they are, aligned with a probability of 0. The graph here has a weight of 2 and a bias of -2. It's frankly not a bad fit to the data. The 3 red points on the right hand side would be classified as defaulters and all the green points would be classified as repayers. The 2 red points in the middle would likely be above the threshold and hence correctly classified. This leaves just the 2 red points to the left, which would likely be misclassified as repayers when they do in fact default. By changing the parameters of our sigmoid, we can change the characteristics of the classifier. Here we have a weight of 5 and a bias of -7. This is perhaps too conservative. While it correctly classifies all of the actual defaulters, there are too many false positives and all of the actual repayers would be misclassified. So a further shift of parameters to a weight of 1 and a bias of -21 has frankly the opposite problem. No false positives, but too many false negatives. We need to find an optimum weight and bias. A good match for this data is a weight of 1 and a bias of -15, as can be seen in the chart on your screen. The goal of our training phase is therefore to use our training data to get a value of W and a value of B that minimises our false positives and our false negatives. Before we look at how we train our logistic regression algorithm to optimise these parameters, let's first make the analysis a little more realistic by adding a second parameter. To visualise this, we'll use a 3D chart. Our probability of default will be on our z-axis, and our 2 input values, in this case the debt to income ratio and the overdraft ratio, will be on the x and y axes respectively. As before, we'll colour code our training examples, red for defaulters and green for repayers. As you'd expect, defaults are more commonly associated with borrowers that have large debt relative to their income, as well as large utilisation of overdraft facilities. If we overlay our sigmoid function, this forms a surface with a diagonal decision boundary separating the data. As before, we can get a better illustration of the classification by moving our defaulting samples up on the z-axis, consistent with a default probability of 1. In exactly the same way as for our 2D case, we can adjust the weights and biases of our sigmoid function. This will shift, flex and morph the surface, moving our decision boundary. In so doing, we can find a set of parameters that give us the optimum F1, accuracy, precision or recall scores. Let's take a quick look at how we go about this. Firstly, let's look at our sigmoid function when we have a single input x. It has 2 tunable parameters, W and B, that we can tweak to improve our results. If we extend this to 2 inputs, in this case x1 and x2, then the equation is in this form. We now have 3 tunable parameters, a weight for each of our inputs and a single bias. We can easily express this equation in a vectorized form. This allows us to cope with as many input parameters as we wish. For our training set, we will have a set of inputs labelled X, and our target output, our output here, is whether the borrower defaults or not, and we'll denote that as Y. We want to choose our weights and biases such that the error between the predicted probability of default from our sigmoid function and the actual default, as indicated by the vector y, is as small as possible, summed over all of our training examples. As we mentioned earlier, this looks a lot like optimizing our weights and biases for neural networks. Indeed, it is. We will use the same method to iteratively nudge these parameters so that they converge on an optimum solution. The method is called stochastic gradient descent, or SGD. If you're unfamiliar with SGD, then I encourage you to watch Lucidate's videos on the topic. These can be found at the URL on the screen or the link in the description. Simply stated, SGD uses calculus to derive an iterative equation to solve for the weights and biases. A learning rate, shown here as alpha, allows us to trade some accuracy for speed in terms of convergence. These two equations allow us to solve for our bias B and our vector of weights W. If we look at how logistic regression performs on our loans dataset, we can see that the performance is very similar to that of our k nearest neighbours and our tree analysis. Logistic regression is simple to implement, easy to interpret, and compared to techniques like neural networks, very easy to train. However, it enforces linear decision boundaries and can find it difficult to model complex relationships. For more challenging classification tasks with non-linear decision boundaries, more robust results can be obtained using more complex solutions such as support vector machines and neural networks, though these methods take more time to train and have more complex sets of hyperparameters. Nevertheless, logistic regression is a great tool for simple classification problems and small data sets. In this video, we've looked at binary choices, but it can be easily extended to deal with multi-class, multinomial regression. This is Richard Walker from Elucidate. Please join me for the next set of machine learning videos where we explore ensemble methods and boosting.